guys, now we can just start the next class. So in the previous class I just told about what is casting and a little bit of extra thing I just mentioned about you in previous section. So in this section we are just going to see the next thing, because this is second lecture. And welcome to my channel. My name is Raman. So without wasting time, let's get start. The first thing, you can see the pouring temperature. The most important controlling factor of pouring temperature is amount of superheat, because superheat I would have already mentioned. For example, just only suppose the aluminum melting temperature is 660 degrees Celsius. So while you are just pouring into the flask or anything, you can see this is 660 degrees Celsius. Let's reduce 657, 650, like that it will goes on reducing. So instead of pouring at 660, we need to pour 700 degrees Celsius. So I think so whenever it reaches the mold inside, it will reaches 60 degrees Celsius. That's called amount of superheat. Okay. Higher the pouring temperature and higher the fluid rate, definitely. Excessive temperature means so much. Instead of pouring at 700 degrees Celsius, I pour at 1500 degrees Celsius. Means excessive temperature should be avoided. However, at the high pouring temperature, metal mold, it means metal, it means the pouring metal, as well as the mold, that means the sand, as fully accepted, and the fluidity, it means penetration. So the fluid may get, it means the sand that's been surrounding the thing will get sticks to the fluid. Okay. So for example, if this is entirely sand thing. So if I'm just pouring at 1000 degrees Celsius, this sand gets sticks to the fluid, and the entire the mold, it means what kind of product we need, that will get damaged. So penetration is referred where the metal not only fills the mold cavity but also fills small voids, okay, between the sand and particle. I think so you can see. So like this only we need. You can see this one blue part. But actually, as the melting temperature is so much, you can see it's how the shape is being changed. Like that it will just become. Okay, effect of variation parameter in fluidity. One thing is increasing pouring temperature, definitely fluidity increases. Increase in viscosity, yes. Increase in viscosity means you can see my two hands is without I can just move freely. But you can see now when I just apply the pressure, it's so much difficult. So viscosity means layer by layer flow. So when viscosity increases, definitely the fluidity decreases. And as well as the increase in density increases, also viscosity decreases, means the fluidity decreases. And increase in percentage of water in sand, it means increasing percentage of water in sand. So you can see the fluidity decreases. Okay. For example, I think so you would have seen about the floor. Floor means wheat flour, like that. So when you add it means water, it means you can see the floor gets to the rounder shape, but after certain amount of time the floor doesn't move on. It means the wheat flour that is used for chapati doesn't move on, but after a certain period of time, each and everything, the entire thing just neatens in the fluid. So at the beginning, it is increase in percentage of water inside decreases, and increase in surface cavity, surface finish of the cavity further increases. For example, the molding property is like this, rough means the fluidity doesn't go so much usually, but if the flow will be so much smooth, the fluidity goes. Okay. And the cavity would mean the fluidity goes well as over, and cavity damage fluidity less. And hot metal mold leads to evaporation, because hot metal mold leads to evaporation of water, absorbs latent heat and reduces fluidity. Okay. The next thing you can see, in sand casting, fluidity of a molten metal increases. In sand casting, fluidity is increasing superheat, definitely increases superheat, because superheat is so much important. And fluidity in the casting operation is greatly influenced by melting temperature of the molten metal. Okay, melting temperature, but instead of pouring temperature is the most important thing. So pouring temperature will be the most important thing. The next thing you can see, the fluidity of molten metal on the casting without any additional value increases with increasing degree of superheat. Okay, surface tension, viscosity, no. Viscosity decreases, freezing rate, no. So next one, I think I already told you about what is core. So core is used for making cavity and a hollow projection. All sides of the core are surrounded with a molten metal and therefore subjected to more thermal, it means more stress. So for that, the core sand should be so much in a higher strength. Okay. Why I am just telling this, because for example, I am just going to make a pipe of like this. Okay. So what I'm just doing, I'm just making the entire thing like this, and making the core like this. Okay. So here the entire the thing is being present like this. This is core. Core is used for manufacturing the internal diameter. So you can see guys, now I'm just serving the fluid here. So you can see in this core, the fluid, it means the pressure will be so much high. Pressure, the degree of superheat is so much higher. So here it is normal sand. So the core sand should should withstand higher temperature and higher degree of pressure like that. So severe thermal stress will be, so the core strand should be so much higher. So that's why their core strand should have a higher strength than the molding strand. Okay, molding strand difference, core strand is different. Okay, you can see outer thing is, this is molded metal, and you can see this one. So why I am just saying is sometimes while the thermal stress has been occurred, you can see this core has a diameter of, for example, 100 mm, and this, while the thermal stress is being imposed on the core sand, this 100 mm goes to 99 mm or 98 mm, that also is going. Okay, I think so you can understand. And if I think so you are getting the point. And the next one is green strength. Green strength, the core made up of green sand should be strong enough to retain the shape till its core breaking, yes, definitely. And dry strength means whenever it doesn't have any kind of, for example, I think so you would have sound about the wood powder. So wood powder doesn't have any kind of vapor or any kind of moisture in it. It's called as dry. So dry strength also, so that the core is placed inside the mold, so it should be able to resist the metal pressure acting on it. Okay, I think so agree. So next one is refractiveness. Since in most cases the core is surrounded all around, and it is desirable that the core material should have higher refractiveness. Okay, so refractiveness is not a bigger thing, so I'll just show you so you can have a clear cut understanding. So you can see the quality, it means refractiveness refers to no resistance to influence. Okay, material ability of the ability of material to resist deformation or melting at higher temperature, often used to describe the refractive bricks. Okay, the ability of material to resist deformation or melting at high temperature. Okay, I think you are getting mine. Since most of the cores you should have also, for example, whenever we just pour the molting, which means the temperature, right, this core sand should have higher refractiveness. So since it has higher refractiveness, means definitely it can hold and it can withstand so much of huge temperature, and the stress, dimension, each and everything can hold. So it's just a resistance of the, it means how much the temperature we put is just a resistance, that's it. So next one is permeability. Permeability is, you can see, gas evolving from the molten metal and generated from the mold may have to go through a core to escape the outer of the mold. So permeability means, for example, like this it is with that. So I'm just placed here the molten, it means the core sand, and here the entire cylinder should be made. So you can see while this being because the fluid is also, while we are just pouring there is a fluid, so in that small it means bubbles, it means small air bubbles will be. So the air bubbles should go to the core like this, or it may go to the molten sand and should go out. So the permeability should be there. Okay, it's like a escape passage, that's it. Okay, so the permeability, gas evolving from the molten metal generated from the mold may have to go through the core to escape out of the mold. So hence core or equator have greater weight. So there is another thing called permeability number. Okay, permeability number, it means for each and everything the permeability number differs. The rate of flow of air passing through a standard specimen under standard pressure is termed as permeability number. Okay, I think so. For each and everything the permeability number is there. For only one thing like that, it is not there. So you can see the next one. The standard permeability test is to measure time taken by. You can see the standard permeability number is to measure time taken, because this is just a standard experiment. Okay, the main formula is this one. Permeability number R equal to VH divided by PAT. Okay, this PAT. Okay, VH divided by PAT. So V is the volume of air. For generally we are just taking 2000 centimeter cube. Okay, for next one, height is the height of the height of the sand specimen. Okay, this is general case, 5.08 centimeter. So next one is pressure, is this air pressure gram per centimeter. See guys, here each and everything is taken in a centimeter. Okay, so next is cross section area is, okay, this 20.26. So while we have just calculated in this thing, so R equal to 501.28 divided by PT. So P is pressure and T is second. Okay, time in minutes. So okay, so each and everything is taken in centimeter as well as a gram, but this time around is being taken in minutes. Okay, I think so. I'm getting the point. So So for example, you can see in this thing they will do like this. So like this, mention this is a sand, molding sand. Here we will just apply the pressure. So you can see here the air is there. So this air should pass through this molding sand. Okay, this entire volume is 2000 centimeter cube, and gravity and the pressure we need to apply, and area okay, and time, it means how much time it taken to move the entire outside. That's it. In minutes we need to just time. Okay. So here they have just asked a question. You can see calculate the permeability number. So you can see calculate the permeability number. Calculate the permeability number of a sand if 1 minute 25 seconds to pass volume 2000 centimeter cube, and at a pressure of 5 gram per centimeter through a standard cycle. So we need to just convert in minutes. So R equal to PVH divided by P A T. Okay. So since it's been given, calculate the permeability number through a standard, they have just given standard sample. So you can just take 501.28 divided by pressure into time. So time is 1 minute 25 time into 1 minute plus of 25 divided by 60 minute. So while they are just calculating how much, 1.416 minute will come. Okay. So 501.28 divided by pressure is 5 gram per centimeter cube into of time is 416 minute. So while they are just putting and calculating, 70.75 is coming. That's it. Okay. So next one is, you can see collapsibility. At the time of pulling casting strings, yes definitely. At time of pulling casting, unless the core has a good collapsibility, ability to decrease in size. Okay. It is likely to require resistance against shrinkage and thus can cause hot tears. Okay. Okay. For this case, we don't add clay. Okay. Which clay is So why we don't use mostly in the clay? Clay doesn't, it means it doesn't strings or doesn't allow any kind of pathways. So however it remains as it is. For example, if the thing is been 50 means it will be 50. But for some kind of other molds, we can just change the shape easily. But for clay we can't change. So the collapsibility for the clay is so much lesser. So the time of pulling casting strings, yes, unless the core has good collapsibility, ability to decrease in size, it is likely to provide resistance against shrinkage and thus can cause hot tears. So next one is friability. Friability is the ability to crunch. It means crumble. Should be very important consideration time of removal. Okay, because how much, it means friability means how much easily we take the core outside, not by beating. For example, I think so I would have showed the video, because how we are just taking the material outside. So that's the thing called friability. So friability should be good. So at the end of thing, we just apply the friability, means we just apply a kind of saw test or kind of food test. So we can just take the mold out easily. Okay. Smoothness, surface of the core should be smooth for good finish, definitely. Low gas emission. Okay, that's also correct. So next one, you can see using sawdust. Sawdust means that wood dust we are using. So we'll just spray over that. So next thing is more gas in core. Okay. So since you can see gases, so means molding more than goes high. So gas in the core should be always less. Okay. I think you can understand. So the next thing is, you can see the core sand. Core sand, it is used clay free silica sand. Okay. Clay free silica sand, it means, and binder use lime seed oil, core oil, resins, dextrins and molasses. So core oil are mix of lime seed, soya, fish and petroleum oil and the colza. The general composition of the core oil is, the oil is 1% and water is 2.5 to 6%. Okay, that's it. So now we just compare the both of the two things. Net buoyancy force. Net buoyancy force equal to weight of liquid. Weight of liquid metal as a weight of core material, core displaced. Weight of total weight of, it means buoyancy force equal to volume, it means so weight of liquid metal is volume gravity and density of material minus of volume gravity into density of liquid displaced. Okay. So So volume gravity in the middle, so we can have the volume gravity density of metal minus the density of coal. Okay, that is your beginning words. So next one is carbon dioxide molding. So carbon dioxide molding, you can see sodium silicate is used as metal. So this is essentially a quick process of mold or mold preparation. The mold is prepared with a mixture of sodium silicate, sand, and it is generally treated with carbon dioxide for 2 to 3 minutes, such as a dry composition over 1.5. Simple guys, they will just take the sodium silicate, and they will pass the carbon dioxide. Okay, they will just pass the carbon dioxide for 2 to 3 minutes. So and dry within that dry compressive strength of 1.4 megapascal is obtained. Okay, that's it. So you can see the carbon dioxide is expected to form weak acid which hydrolyzes the sodium silicate result in amorphous silica. So this one we need the silica. Okay, the main reaction of carbon dioxide gas starts the reaction by forming hydrated sodium carbonate Na2CO3 plus H2O. Okay, so the compressive strength of the bond increasing with the standing time due to dehydration. Okay? So because of the higher strength of the bond, the core needs to be provided with any other refractoriness. So you can see here, this is called as carbon dioxide molding. Okay, so whenever we just pass the carbon dioxide over it, it gets hardened. Okay, so you can see here, so this is sodium silicate and sand. Whenever we just pass the carbon dioxide, the strength, it means what is this thing, the entire solid gets started. So after getting solid, it means directly the pattern is, you can see. So now we will just pour the indicator of other thing, each and everything. So okay, the compressive strength of the bond increases with starting time. So due to dehydration. Okay, so you can see because of the high strength of the bond, the core needs not to be provided with any kind of other refractoriness. Okay, so it doesn't involve any distortion due to baking, and also better dimension accuracy is obtained. So the sand mixture does not have good shelf life, and therefore it should be used immediately after preparation, because instantly we need to use this kind of carbon dioxide. Okay. So they just asked only one question here. So you can see in carbon dioxide molding that the bind used sodium silicate. That's it. So in CO2 casting process, the mold on the core attains vacuum pressure. That's definitely. So the optimum gassing time CO2 through mold and non-silica, which implies sufficient strength. Yes, definitely. So it is the correct one. So you can see the next one and get to some of the ask. Yes, sand in a sand casting of cylindrical core. Okay. Density. The diameter and the height is given. Okay. So the density of the core meter and is okay. So the net force, so they are asking the buoyancy force. So P equal to volume to gravity, density of the so C1 pi by 4 d square into height into 9.81 into density of mold is 113 minus 1600. So what will be 0.14 into 36.12 into 0.12 into 0.18 into 9.32 into 11300 minus of 1600. So what is the answer? C is the answer. Okay, 193.7. So directly we got the answer. So next thing you can see get is been as same. So cylindrical 100 diameter and length is given cylindrical hole. Okay, so the same thing was volume, gravity. You can see this one. So we can just directly get the direct answer. Okay. So next one is called as molding sand composition. Sand is ordinary silica sand, SiO2, means generally we are using is zircon also in aluminum solid slow clay, act as a binding agent mixed to the molding sand. Okay, clay will just act as a binding, just a mixture as I said. So next one is water. Clay is activated by the water. Okay, so these are just extra thing. It means sharp water blast and pitch is used up to 3% to improve the cord strength. Okay, cereals when used to increase 2% of the strength. So another material is C1 and graphite and process, each and everything will be used. Okay, so generally we need to see lot of questions in this chapter guys. So the next thing is you can see these are extra and extra thing that has been given, and the next thing is you can see the porosity or permeability. Porosity means you can see it's definitely the small the air that means that should flow. So you can see permeability or porosity of a molding sand is a measure of ability to permit air to flow through it. Okay, that's the most important thing in this casting. And next one is strength. Strength, it is defined as the property of holding together of sand mold, because for example this is a sand means you can see this is a, it means mold that we need to just pour each and everything and to make a material, and this is a sand. So the sand should also have a certain strength, because sand is strength is just a grain of particles, grain. So it means if the grains capacity increases, then definitely the sand's capacity also will increase. So there should be strength. Strength is defined as the property of holding together of the same sand. A molding sand should have ample strength so that the mold does not collapse and gets partially destroyed during, it means while we are just turning, while we are just pouring the, it means pouring the fluid. So mostly the sand it gets also destroyed, so we need to just take care of it. So as I just told about you this thing, so you can see whenever we just increase the water content, it means you can see the permeability. It means permeability increases, means the flowing of air, it means the flowing of water also increases. Okay, so the next thing you can see here, here you can see permeability as well as the flowability is given. For example, when you just add a water, you can see the permeability increases. It means okay, it means the air tends to go outside, but whenever you just add extra amount of water, the entire permeability decreases and it does not allow any kind of any kind of air to go outside. So next thing you can see the flowability. So at the beginning there, whenever the water is less, you can see whenever the water is less, for example the chapati flour, it means whenever it just, if you just add a little bit of water, you can see how much the, it will just show to you. So this is you can see guys, whenever you just add it means extra amount of water, you can see that round shape it will come. So but later on what will come, it means later on when you add excess amount of water, the entire thing, it means the flowability will increase, it will turn to the liquid state. So generally water should be within 6 to 8% within it, so we can just give, that's it. So next one is refractness. I just told the word division before this. It means the sand should have a good amount of refractness, because if the sand has good amount of refractness only, it can have the ability to withstand the surrounding temperature. Okay, it is a bit of molten sand mixture to withstand the heat of mold without showing any sign of softness or fusion, because fusion means if the sand gets deprived, it means with the outside and it will just mix with the surrounding fluid. Okay, so next one, plastic. Plastic is a measure of molding sand to flow around, okay, and over the pattern during ramming and to uniformly fill the flask. Okay, it means plasticity is the ability of molding sand to flow around. Okay, whenever you just so just to show you video, so you can have a little bit of molding. So you can see like this, they are just making. So see, now you can see whenever he just rammed here like this, see that's it, it's been finished. Okay, so you can see whenever so you can see the ramming has been done, and you can see the molding sand to flow around. You can see the molding sand should be placed perfectly here. So over the pattern, this is the pattern over the pattern during ramming, so to form uniform thing. Okay, I think so, I got the point. So So next one is collapsibility. So collapsibility is the ability of molding sand to decrease in volume to some extent under the compressive force developed by the shrinkage of metal during it means or is the ability of molten sand to decrease in volume. Okay, it means ability of molten sand to decrease in volume to some extent under the compressive force developed by the shrinkage of metal during freezing as well as the subsequent cooling. Because you can see guys, the it means how to say means because the collapse is the most important thing. For example, this is core. Okay, the core sand is it means for example this is made up of sodium silicate. Sodium silicate whenever we just passes like this is so we need a like this cylinder. So this is a molding sand is based and we just pass the CO2. So the mold it means the aluminum metal goes and passes over this and it's been fixed in a good shape. But what's the main issue is this is a molding sand, this is a core sand, this is made of sodium silicate. Now what we have just passed here carbon dioxide. So this sodium silicate and carbon dioxide this especially gets so much harder. Well, okay, so it doesn't compress, it means it doesn't just shrinks. If it doesn't shrinks means you can see this entire thing will get collapsed and will just form like this. Okay, it means instead of being like here you can see in this area it will just tilt to like this area, a little bit of increase, it means the outside volume will increase. Okay, so the core should have a good collapsibility, it means each and every molding cell also should have the collapsibility, it means should little bit decrease in volume to a certain extent under the compressive force always shrinkage of metal. Okay, so next one is adhesiveness. Adhesiveness I just told you about you the property of a sand mixture to another body, here is mold flux. So the adhesiveness should be good. Okay, the sand as well as the molding flux. Okay, that's it. For example, if this two has a good cohesion means this gun may sticks with the sand. So due to the good adhesion, because this and this attraction is formed also, so that's why adhesiveness is must be there. So next one is facing sand. Facing sand in this they would have shown to facing sand. So you can see he just sprays some kind of oat powder. So now we'll just pour it again. So that is called as facing sand. So now I think so you can see this white powder. So that's called as facing sand. Facing sand is a small amount of carbonous material sprinkled in the inner surface of the mold to give better surface finish. Okay, facing sand is just used for better surface finish. So you can see next one backing sand. Backing sand means waste sand, that means used techniques. So this is made up of it means used or burnt sand, that's it. So next one is green sand. Green sand, the mold sand that contains moisture is termed as green sand. Whenever the thing consists of moisture is called as green sand. So the green sand should have enough strength so that constructed mold remains its shape, that's it. So dry sand is mean dry sand moisture is not there, that's called as dry sand, that's it. So small carbonous materials sprinkled in the surface is called as facing sand, right? So next one is this green sand. Mostly this doesn't have but generally you need to read. So you can see this one, the grain size number. So n capital equal to n minus small n minus 1. So n is the number of grain per square inch visible in a prepared specimen at 100x. Okay, so the next small n is the grain size number. Okay, number of grains is n is number of grain. It means for example this square box contains of 1000 grains. Okay, 1000 grains. Okay, this square box contains 1000 grains. So this n is 1000. So small n is for you can see grain size number. For example, this grain has a certain n number and this grain size has a certain n number. This grain size has a certain n number. So that is called as grain size number. Okay, so n equal to capital N equal to 2 power n minus 1. Okay, so I think so you are getting the point. So it's just a simple thing. So the next thing is you can see what is the thing. So option B is the right one, n minus 1. Okay, so this is at 100x. Okay, so in this what is the you can just find the n also, because if you know the n, it means number of grains means you can just calculate the grain size number. So simple. So next one is sand slinger. You can see this is a kind of sand slinger. So you can see the sand is being poured over here. So you can see this is the pattern. Okay, instead of this is the pattern, and upper to it we'll just slide, we'll just pour the sand over it. Okay, this is called a sand slide. We need it means here we no need of any kind of landing. Okay, next one is molar machine. Molar machine, I just showed you molar machine. So you can see like this it will be, and the so like this it will be, and we will just pour the sand and anything else and kind of other material, so it will just get so you can see this way. So you can see like this only the Muller machine will be. So in this we will just pour the entire the sand and each and everything. So you can see at the bottom the sand is getting mixed. Okay, so the sand should have a good mixing strength. So next one is the casting yield. So one of the most important, because why I'm just telling is again you just see this one. So he just pours this under. And now you can see guys, now we just need the round shape alone. Okay, you can see this thing is waste material. We need this round shape alone, this round. So this extra thing is a waste material, you can see. So this extra thing is a waste material, so that comes in the category of this one. Which one will be perfect? So you can see we need this portion alone. Okay, so we need this portion alone. So this riser part, so this riser part, this running area, this poo area is not effective, it's not in order. So after getting the mold we'll just cut this, that's it. Okay, so that's kind of the casting yield equal to W by capital W into 100. So what is the W? Which is just a weight. So first in the upper portion is weight of casting, weight volume of casting divided by volume of casting plus the volume of gating element, Okay, so volume of casting is the main mold area, means what we need. So this is the mold area, this is the sprue, runner, ingate as well as the riser. Okay, at least you are getting a point. So the next thing is you can this pouring basin, sprue, the ingate, and you can see this casting area, this is the riser. So this kind of thing we need to just consider. So next one is the gating system. The pouring basin should be a small funnel shaped cavity at the top of the mold into which the mold metal is poured. Next one is sprue. Sprue, the passage through which the molten metal from the pouring basin reaches the mold cavity. In many cases control the flow of metal into the mold. So next one is you can see runner. So runner is a commonly horizontal channel which connects the sprue with the gate. This allows the molten metal to enter the mold cavity. The runner are a large cross section and often streamlined through slow down. And see the most of the thing, and the other thing is you can see runner are commonly made of trapezoidal in shape. Trapezoidal. Trapezoidal in shape. So why? Because so trapezoidal means like this it will be. Okay. So mostly it means the runner is should be like this. Suppose we just provided like this, means you can see here the accumulation of material will be more, and you can see the accumulation of material is lesser. Okay, as I just told to you before, how I just told you, here the pressure will be less, here the pressure will be, it means here the pressure will be more, here the pressure will be less. Okay, this is the right thing. This one we should, you can see here the pressure will be normal, but here the pressure will be higher, so here the pressure will be lower. So suppose high to low only, so the pressure, it means when the material passes here, the pressure will be just pushed like this, so the metal will just go like return back. So you can see here the entire thing pressure will be high, it means pressure will be here like this, will be just place the runner. You can see now the pressure will be, so here higher thing, here low, so high to low. So now the entire thing will just push this way towards the right side. Okay, I think so you are getting the point. So runners are commonly made of trapezoidal in cross section. Okay, so next one is this one is the ingate. It means this is just the entry, so a channel through which the molten metal enters the mold cavity. That's it. Vent is a small opening in the mold to facilitate escape of air gaps. That's it. So the main thing is choke area, the main control area which meters the metal flow into the mold cavity so that the mold is completely filled within calculated pouring time. So the controlling area is called as choke area. So normally choke area is at the bottom of the sprue. Okay, bottom of the sprue. Hence the first element to be seen is the sprue. So the sprue area is so much important. So sprue area is so much important. You need to just control that sprue area. So what is the main formula of the choke area is? Choke area is so much minimum amount of area. So mass, okay, mass of the casting divided by, it means density of time root of 2gh. That's it. Okay. So how I can just release Q equal to area into volume. So it means discharge equal to area into volume. So so Q equal to mass flow rate m dot, it means mass by time. So this one m divided by time equal to area into area like this, and volume is density. Volume is density to mass will just density equal to mass by volume. So volume equal to mass divided by density. So this Q we need to write in another format. So okay. So this, because this is area into velocity, meter cube per second. Okay. This is area into velocity. We'll just write again. So area into velocity equal to Q. So Q is, I think so, by this is just a basic explanation. Based upon this only we'll just calculate each and everything. I'll just show it to you in a better format. Oh, it's not been present, guys. Okay, then just leave it. So it's just a normal calculation. So just choke area is equal to mass divided by CD, it means density into time root of 2gh. Okay, that's it. So density is density of metal, and T is a pouring time, because pouring time. So CD we just is an effectiveness factor. It's a function of getting clean. So next H is a effective head of liquid metal. So H is the top gate. Okay. So next thing we are just going to see top gate and bottom gate. So top gate means, it means from here the mold comes in ports like this. So bottom gate means from here the mold get enters like this. That's the thing for the top gate and bottom gate. So in top gate what is happening is causes surface, because here you can see splashing of liquid directly, it will just comes in for splashing of liquid occurs. Okay. So and it is prone to form towards favorable temperature gradient is towards the gate and only for feathers. So top gate is a TF, so only for feathers, or FT or TF like that you just mentioned. So top gate is used for only favorable temperature gradient. So bottom gate you can see no mold erosion, and used for very deep mold and causes no turbulence and splashing. Higher pouring time, definitely it's a higher pouring time and causes unfavorable temperature, because you can see here the temperature, because you can see the temperature will be same here, but here the temperature will be unfavorable. So while it's been increasing, it gets cooled faster. This 100 degrees Celsius, this 120 degrees Celsius, 130 degrees Celsius, 150 degrees Celsius, like that it will be. So this bottom gate is for non-porous, non-ferrous material we just generally use. Okay. So next time is parting gate. So most widely used gate, easiest and most economical in preparation, can be used for ferrous and non-ferrous alloy material. Okay, that's it. So it means we can just use for both ferrous as well as non-ferrous. So next one is step gate. Step gate is a heavy and largest casting, and size of the gate means step gate is, you can see step gate while the top gating, bottom gating, middle gating, and parting gating. Parting gate is just to use as a, it means middle section. That's it. Okay. So while each and everything goes, I'll just explain to each and everything. So you can see this temperature gradient is so much more, but you can see Here the down will be higher temperature and the upper will be lower temperature. So here the mixture means at the bottom again here mixture of the material doesn't grow in a proper way. So that's why we need to just consider. So next one you can see in light metal casting runner should be designed that like runner okay runner. So it must avoid aspiration is definitely okay should be okay, it avoids turbulence okay. The path of runner is reduced so unparalleled. So what is the answer C? Because aspiration, so generally the sprue area should remove the aspiration. Aspiration means for example whenever it means whenever it's been like this, so it means as I just told to you before here the pressure will be higher, here the pressure will be lower okay. So whenever you just see here you just go like this, so here the pressure is higher, here the pressure is lower, so here the velocity will be higher. So you can see the higher thing will go like this. So after that what will happen here, it's been you can see here it's been P atmosphere and wait, I don't want to make you confused, but the concept is clear. So here it's been open to atmosphere, P atmosphere, but you can see as continued equation P1 V1 equal to P2 V2. So continued equations other thing okay. So you can see whenever we just go down, since it's been a nozzle, since just I explain to you again. So you can see this is entire thing is sprue area and here the P atmosphere will be, but as you go down pressure drop will occur. So like this and it will go to the mold area. So you can see the entire thing will be like this. This is sand. So here the pressure will be pressure less, pressure low, pressure high. So you can see high to low it flows okay. So you can see surrounding area is also been P atmosphere. So goes like this. So while it's been going, it will take the air molecule inside and it will just go and join here. Okay. So now the air just goes in here. So this is because it's been considered only in the sprue area. So runner area is minimum. You can see runner area and the choke area. You can see this is the choke area. So choke area, runner area, and ingate area. This is the ingate area. It's all minimum. So here the aspiration doesn't affect. You can see since the entire thing is like this in the sprue, the aspiration affect it means mostly occurs in the as it means sprue okay. Yes, runner should be placed okay to avoid the turbulence is definitely. And next in the path of runner is reduced in area so that unequal volume of flow through each get passes to the extenders okay. So next you can see this one during the filling process of the mold cavity towards the frictional head loss of metal is in the runner. So the basic thing is you can see H equal to 32 mu V average will be rho G D square okay. So they are asking the means during the filling measurement through the horizontal runner cross section the frictional head loss of the molten metal in the runner. So the friction will increase when okay increase in runner diameter. If we increase in runner diameter, the friction loss will decrease and decrease in length okay. So increase in average velocity, you can see this when we just increase this average velocity, the friction will just increase okay. So next thing you can see about this question. I think so you are seeing this one. So top gate is generally used for favorable. So top gate is yes definitely it leads to turbulence. Bottom gate is unfavorable. Parting gate is mostly heavy and parting gate is mostly used for okay. Most parting gate okay. Step gate is used for heavy and large turbulence okay, because you can see step gate is used for heavy and large casting and size of the integrate. So in this they are asking this one, what is this one? AB, this is sprue and this is riser, that's it. So the primary use of sprue in the feed the casting in the constant bed with a constant. So feed the molten metal from the pouring cup pouring vessel with the reference this one. So the goal for gating system to minimize turbulence to trap to minimize turbulence to get enough metal into the mold cavity before the metal starts shrinkage. Okay. Next thing, to avoid shrinkages definitely. So the goal for the gating system, establish the best possible temperature gating in the solidification is existing is okay. This one okay. So they are not incorporates the system for tapping non okay. So the next thing you can see, ideal document of the gating system. Water metal should enter the mold metal cavity with a high velocity. Oh, this one is a little bit dangerous. It should facilitate the complete filling of facility. It should be able to prevent absorption of the gas and sounds of yes definitely. So and this one okay, this one the mold action through the motor metal the motor is simulate. Bottom gauge is unfavorable as reference. Spool is a case made of tapper to avoid air inclusion. So it's made tapper to avoid okay the mold is to avoid made tapper. So tapper will not be to avoid okay. So option 1 and 2 is the right answer. Okay, we can just go to the next question. So next one you can see tapping of gating system. So there are two types of gating system. One is pressurized gating system. Second one is unpressurized gating system. So both are not a different thing. Both are just the same things but a little bit different. So you can see as I just explained about this concept, the same thing. So in pressurized gating system, it will be like this. So you can see in this P-ATM will be there, but here only the P-ATM will be there. So you can see in the glucose here the entire thing will be of lower pressure. Here the entire thing will be higher pressure. So higher pressure will just push the molten metal towards this and it will just fall. So the total cross section area decreases towards the mold cavity as definitely. Back pressure is maintained by restriction in the molten metal. Flow of liquid is almost equal as definitely. Flow of liquid is almost equal in every case. So the back pressure helps in reducing the aspiration as definitely, as the sprue always runs full. So there is no problem of air aspiration because of the restriction the metal flows at higher velocity. Yes, leading to more turbulence. Yes, definitely. Because you see as the pressure decreases, the velocity will be higher. So as the velocity higher means the velocity will go and hit the area, and hit the object. So more turbulence and chance of mold erosion occur and can be used for top gating. It means erosion will occur. That means turbulence will occur. So for same pressure is getting also the turbulence is will occur. So it is used for it means ferrous material. So casting yield is more. Yes, this one is pressure yield, casting yield is more. So volume of casting will be volume of casting plus the volume of the gate materials. So next one unpressurized gating system. In this you can see the total cross sectional area increases towards the mold cavity. Okay, the total cross sectional area increases to, you can see this like this will be. So here the pressure will be lesser, here the pressure will be higher. So here the pressure will be higher, here the pressure will be lesser. So the flow will occur. So definitely lot of problem will occur. So restriction at the bottom of the flow of liquid is different. Yes, definitely flow of liquid is different. Okay, this is unpressurized gating system. Aspiration in the gating system as the system never runs full. Definitely less turbulence can be used for non-ferrous metal. Casting is very low. Casting yield is for unpressurized is less. Okay, so next one I think so you don't see this one. I just okay, you can see the total cross section area decreases towards the mold cavity. Next one is more turbulence and chance of mold erosion. Flow of liquid metal is almost equal in all gates and casting is more. Complex and thin section can be successfully casted. Yes. So gating ratio is 3 to 1. So gating ratio I just tell you that in letter. So gating ratio is 3 to 1. Air aspiration is minimum. Volume of metal is almost equal. The small volume of casting is velocity is higher. Okay, so same to is opposite. So less here more turbulence, less turbulence. So metal is same, flow of metal is same. Here this is casting is more, casting is less. So small and thinner section, complex and thinner section, difficult to cast, complex and difficult because it's so much. So thin section we can't do and complex section we can't do. The gating ratio only to do is and aspiration, each and everything is same. So I think so I'm getting the point. So with this I will just complete. So next one is a sprue design. So sprue design, you can see sprue is a channel through which the Molten metal is passed into the parting line which renders a runner and the gear to ultimately reach the molting area. The molten metal when moving from the top of the core to the parting line gains in velocity, and so low pressure area has been created to surround the gas definitely. So since the sand mold is permeable, atmospheric air would breathe into the low pressure area, so which would be carried to the mold metal. To eliminate this problem of air aspiration, the screw is tapped. You can see like this. We will just make it tapper. Okay. See why I am just telling this before. It will be like this. So while the molten metal is being poured, so as it goes like this inside, so it doesn't sticks here. You can see here, it doesn't sticks here. No sticking. Here no sticking will be. Okay. So as it's been no sticking here it's been there, so it will be little problem. So that's why we just use like this kind of tapper. Okay. So here the high pressure will be, here low pressure will be, but when you compare to this one, the air passes here and air passes here. This one is far more efficient. This is here B, so B is more efficient than here. Okay, this one. So then you can see here continued equation. So here A1 V1 A2 of V2, that's it. Okay. So how much liquid comes in, the same much. So suppose here the 10 meter cube comes in, and here also 10 meter cube will just go. That's it. So, okay. So for example, if we just want to find the velocity, means here the pouring cup will be, we just pour here. So this one is H1. So this entire thing is H1. So V equal to root of 2g of H. Okay. For V1 this H1. Root of 2g of H1. So you can see for V2 this is H2. So V2 equal to root of 2g of H2. Okay. That's it. Okay guys, from tomorrow we'll just look out the problems and we'll just go in effective and sooner. Okay. Okay guys, then I'll just see you in the next video. Until then, take care, bye bye, have a good day.